Okay, this is the video that you've all been waiting for, even if you didn't realize it. This is basically an easy way to get any vector into component form. And the beautiful thing about this is when a vector is in component form, it's very easy to find the sum of the vectors, to find the resultant force or the resulting velocity or any of those applications. It's very easy because you just have to add components. There's no law of cosines or law of sines or anything like that. So this is really, really nice, and it's very, at this point we're in good shape to see why this is. So basically, let v be any vector with a magnitude of v here and a direction angle of theta. The component form of v is simply given by the magnitude times the cosine theta and sine theta, which could be written in this way, where the x component, or the first component, is the magnitude of v times the cosine theta, and the y component is the magnitude of v times the sine of theta, which really makes perfect sense because of, if you think about the polar coordinates, very similar here, that the x and the y were r times cosine and r times sine. It's very much related to that. And basically the idea here is the theta is spinning around the unit circle, and wherever it stops here, you get the unit vector, which is just cosine theta, sine theta. And then what you're doing by multiplying it by the magnitude of v is you're taking that unit vector and scaling it so that this vector has a magnitude of v, which is what you want. So this vector then is going to be the component form of a vector headed in that theta with that magnitude. Very, very easy. So the only thing here that you got to be very careful of is that the angle has to be the angle that's measured from the x-axis going counterclockwise, just like when you're doing trigonometry with the unit circle, because it's based on the unit circle trigonometry. So let's try a few examples here. So basically, let v be a vector with a magnitude of 10 with a direction angle of 250. So if I want the component form here of v, no problem. I just take 10 times the cosine of 250 degrees and the sine of 250 degrees, which I could rewrite that 10 times the cosine of 250 degrees, 10 times the sine of 250 degrees. And then if I want to get a decimal approximation here, then I can put this in my calculator. 10 times the cosine of 250 degrees is, or I could do approximately, negative 3.42, and 10 times the sine of 250 degrees is negative 9.40. Just like that. And let's see if this actually makes sense. So 250 degrees. Okay. So if I measure here 250 degrees from here, okay, the lower y-axis, that's 270 degrees. So it would be something like this. 250 degrees would be like that. And then the magnitude of this vector would be 10. So it actually makes sense at this point here, negative 3.42 and negative 9.40. That actually makes pretty good sense. Okay? Just like you would expect. So, very, very nice. Very easy way of getting the component form when you're given the magnitude and the angle. Isn't that nice? And then you can just find those, add them together, by just adding the components. You kind of maybe are frustrated that we did it the hard way in the first unit, but I think the person that wrote this textbook did it like that on purpose so that you would really appreciate this. Okay? So I'm going to do one here, and then I'll have you do the one below. So this says a plane leaves an airport with a bearing of 65 degrees, traveling at 325 miles per hour. Find the component form of its velocity. Now this one with the bearings, we got to be careful here. So a bearing of 65, this is measured here from, so 65 degrees. This is measured from the north going clockwise, but in order to use what we just learned, I need measured from the x-axis going counterclockwise. So I need this angle. No problem. That would be 25 degrees. 90 minus 65 is 25 degrees. So now all I need to do to get vector v for the velocity of this plane is just take 325 miles per hour times the cosine of 25 degrees, sine of 25 degrees. And I could rewrite that as 325 cosine 25 degrees. And of course you wouldn't have to write these steps out every time. 25 sine of 25 degrees. And then, and this would be approximately, if I wanted the decimal form here, so 325 times the cosine of 25, and this is 294.6, and in fact, I think I can just go back and change this cosine into a sine, and then I get the other one, 137.35. And that would be the component form, and that makes sense. It's in this quadrant. This is 325, and this actually would make sense that the x-coordinate is way over here, and that 25 would actually be probably lower down here, and then that's the y-coordinate. So it actually makes sense. So why don't you try this one here? You can hit pause, see if you can find the component form, and then go ahead and resume the video and see how you did. Okay, so let's go ahead and give this a try. So the velocity of this boat, I gotta make sure I get the right angle, so you don't want to use that angle necessarily. Here's north, and I'm going to go around 315 degrees. This is 270, and so that would be 30 plus 15. That would actually be like 45. This would be like a, so I should go like this. If this is 315 degrees, then this angle is 45 degrees, right? And this angle is what we want. We need that angle from the x-axis to here, and that would be 135 degrees. 180 minus that. So I do got to take this and get the right angle. So this is going from north clockwise. I got to find the angle going from the x-axis counterclockwise. So it'd be 135. So I'm going to take 42 times cosine of 135 degrees, sine of 135 degrees. And this would be 42 times cosine of 135 degrees, 42 times the sine of 135 degrees. And so let's see. 42 times the cosine of 135, and I'm going to get this is approximately, this is negative 29.7, and then I'll put in the sign, and I get positive 29.7. And notice those are both the same, and that makes sense because that's a 45-degree angle. Okay, and so that actually makes sense. And the x is negative, the y is positive. So there you go. This is a very nice tool then, and in the next several videos we'll be using it to solve application problems.